Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Last week, I spent some time at CES in Las Vegas, exploring the vast sea of drones, cameras, paper-thin TVs, robots, laundry folding closets, and other smart devices. You name it, it was there. Of course, I was also able to sit down with some really interesting people working on some pretty cool AI-enabled products. Head on over to our YouTube channel to check out some behind-the-scenes footage from my interviews and other quick takes from the show. And of course, be on the lookout for our AI in Consumer Electronics series right here on the podcast, coming soon. A quick note, this is your final reminder about tomorrow's Twiml online meetup. At 3 p.m. Pacific, we'll be joined by Microsoft researchers Timnit Gebru. Timnit will be joining us to discuss her paper, Using Deep Learning in Google Street View to Estimate the Demographic Makeup of Neighborhoods Across the United States, and I'm especially looking forward to her going into more detail about the pipeline she used to identify 22 million cars and 50 million Street View images. As usual, we'll get the meetup kicked off with a discussion segment in which we'll be exploring your AI resolutions and predictions for 2018. For links to the paper, to register for the meetup, or to check out previous meetups, visit twimlai.com/meetup. The show you're about to hear is part of a series of shows recorded at the Rework Deep Learning Summit in Montreal back in October. This was a great event, and in fact, their next event, the Deep Learning Summit San Francisco, is right around the corner on January 25th and 26th. The summit will feature more leading researchers and technologists like the ones you'll hear here on the show this week, including Ian Goodfellow of Google Brain and Daphne Kohler of Calico Labs, and more. Definitely check it out and use the code TWIMLAI for 20% off of registration. In this episode, we hear from David Duvenaud, assistant professor in the Computer Science and Statistics departments at the University of Toronto. David joined me after his talk at the Deep Learning Summit on composing graphical models with neural networks for structured representations and fast inference. In our conversation, we discussed the generalized modeling and inference framework that David and his team have created, which combines the strengths of both probabilistic graphical models and deep learning methods. He gives us a walkthrough of his use case, which is to automatically segment and categorize mouse behavior from raw video, and we discuss how the framework is applied to this and other use cases. We also discuss some of the differences between the frequentist and Bayesian statistical approaches. I had a great time with this interview, and I think you will too. And now, on to the show. All right, everyone. So I am here at the Rework Deep Learning Conference in Montreal, and I am with David Duvenaud. David's a professor at the University of Toronto, and he actually just got off stage. And I'm excited to be sitting here with him, or here with you, I should say, David. Welcome to the podcast.
Thank you, Sam.
So tell me a little bit about your background and how you got interested in machine learning and AI. It sounds like you come a little bit from the statistics side of the world.
No, I've actually been sort of maybe pushed into the stats department. I mean, I'm half appointed stats and CS at the University of Toronto.
Okay.
And it's really nice. No, actually, the way I got into this was actually reading Jürgen Spaduber's webpage when I was an undergrad. And, he had, I think, to his credit, he really was thinking about a lot of things that people, later also found interesting. And he has a way of presenting his ideas as sort of like the last word. I mean, everyone sort of does. But at the time, I didn't really know how to evaluate these things. And I thought, oh man, I need to go to grad school because this guy's going to solve AI in like 2 years or so. So, yeah. I mean, of course, now I have a much broader view. And I feel
so
like
did you go to grad school in Switzerland?
No. Although I certainly looked up this group. I actually went to grad school at the University of British Columbia.
Okay.
Yeah. No, initially, actually, all my friends went to grad school, and my first time I applied for scholarships, I got rejected. And so I had a big chip on my shoulder, and I was like, grad school is for jerks. Then eventually I applied again and got it. And I went to work with Kevin Murphy back when, graphical models were still cool. And, we did a bit of machine vision and things like that.
Okay.
And then he actually set me up with an internship at Google. It wasn't called Google Brain back then. It was actually the video content analysis team. But it was all the same people that ended up forming it. And we just sort of tried to get confidence to predict whether YouTube videos contained people dancing for this contest that YouTube was running at the time.
Huh. Interesting. And so you're now at University of Toronto?
Yes.
How long have you been at the university?
Just a year, actually.
Okay.
Yeah.
And you said you've kind of been pushed into this joint appointment?
Well, okay. That sounds really bad. I just mean that I started off being interested in machine learning and then went and, did my PhD on Bayesian nonparametrics. And I realized that sort of math was the missing component. And, everyone in machine learning has to be able to code and do math, but you really can't get away without knowing the math. And really, a little bit of formalism can go a long way. And especially recently, I've been working on building gradient estimators for discrete latent variable models. And this also shows up in reinforcement learning, where having unbiased gradient estimators is actually really important. Unbiasedness sounds like this boring, horrible thing that frequentist statisticians care about, and it is. But it actually now, I think, is going to turn out to be sort of a central thing that people are going to be worrying about over the next few years.
And so so you just did your talk, and your talk was on combining graphical models with deep learning models?
Yeah.
Tell us a little bit about the talk as an overview, and we can kind of dive into, the different elements of it.
Sure. Well, the way that that paper came about was actually pretty fun. So I just did a postdoc at Harvard with this guy, Matt Johnson, who is now at Google Brain. And when I showed up, I had just sort of deconverted from Bayesian nonparametrics, where I was trying to fit giant infinite dimensional graphical models to everything. And I had started to sort of realize the limitations of these approaches. And I was really excited about variational autoencoders, where we learn a generative model using a neural network, and we also use a neural network to learn to do inference in that model. And sort of, as I said in the talk, people have been able to write down really rich generative models for a long time, but they haven't been able to do inference in them. And that's sort of the limiting factor.
Okay.
With regards to this paper, Matt was coming from a sort of also old school background, where he was saying, I want to use, graphical models, linear dynamical systems, like nice models that we can analyze and understand. And I was telling him, no, you got to forget all of that. You have to just, use neural networks to do inference. We can fit everything with a variational autoencoder. And we had this long back and forth over the course of about a year. In the end, it was kind of my chocolate and your peanut butter. And we had this nice synthesis of ideas. And we sort of said, wait, maybe we can combine these and get sort of the best of both worlds.
Okay, so when you say graphical model, what do we mean with that?
Yeah.
What do we mean by that?
So that's a pretty broad phrase. It basically just means...
It doesn't mean graphics as we traditionally talk about graphics. That's a starting place,
so
right?
The graphical in graphical models means like graphs. And the idea is that initially when people started writing down models, they just wrote down equations that would say what the probability of different things were. And it was pretty hard to analyze these models. And so, I think like Kevin Murphy, Daphne Koller, Nir Friedman, these guys said, what if we actually represent the dependence of different variables as a graph? And, the idea is that if I say that, like smoking causes cancer, then I would have an arrow going from smoking to cancer. And this says something about how the probability of these things change together. So if I get cancer, that doesn't make me smoke, but if I smoke, it might make me get cancer, right? And once we start to have, 10 or 100 different variables, keeping track of all these arrows or these relationships becomes pretty tricky. But when we express these models as a graph, we can automatically analyze them and ask, whether we think that drinking wine causes, better test scores through some complicated mechanism. Or we can also ask, what information would we need to learn in order to tell us what the answer is? Yeah, and so this is sort of this, it's not quite old-fashioned AI, but it's sort of this, we're going to have these rational, understandable models where every sort of human concept has a little box that we put it in, and we try to understand everything that's happening in our models.
Okay, so when we talk about graphs and applying graphs to these types of models, so one of the things that I think of at least is some of the deep learning frameworks like TensorFlow allow you to create neural network architectures using graphs, but that's at a higher level than what you're talking about, right?
Yeah, so that's kind of a confusingly similar idea because, we write down these computation graphs where we have these arrows that mean A is a function of B. And that's also the same sort of relationship we're talking about when we write down graphical models. But in graphical models, the relationships are all probabilistic. We're not saying that A determines B, we're saying the probability of B depends on A.
Okay.
And then the thing we can do with graphical models that we can't do with neural networks so easily is to go backwards and say, given that someone has cancer, what is the chance that they smoked? Which is something, you can't, it's not as easy to sort of run a neural network backwards. But when we run a graphical model backwards, we're sort of asking, what are the hidden causes of the things that we observed? And this is what we tend to refer to as like the inference problem.
Okay.
It's like, how do we figure out how does what we saw change what we believe about what we didn't see?
Okay.
And, this, as an example, you can even view, for instance, like learning grammar. Like when babies learn language,
right,
they hear all these sentences, and there's this hidden thing, which is, grammar and vocabulary and all these rules about how language goes together. And so the problem of hearing a bunch of sentences and then trying to figure out what's the likely rules of that language is an inference problem.
Okay.
And so this is kind of why people have been really excited about these generative models, or like also called latent variable models, for a long time.
Latent variable models.
Yeah, like the idea is the grammar is this latent, unseen variable that we have to infer. And for instance, and also this motivates why people have been so excited by inference. So if you go to NIPS, there's like the Advances in Approximate Bayesian Inference workshop and, variants of it. And it's one of my favorite parts of NIPS because it sounds really boring and dry, but, the inference problem is kind of the bottleneck for doing all the cool things that babies can do that we can't do with, that's at least one bottleneck. Even if we solve inference, there's probably more problems that we need to solve. But for instance, people like Josh Tenenbaum at MIT for, now like 20 years or so have
I
been
need
saying,
to get him on the show. His name has come up probably like 3 times.
Oh yeah.
Just today.
Yeah, and he's just a really inspiring person to talk to because he really saw this vision, a long time ago that guys, if we could just, figure out how to do inference, we would be able to not only explain like how humans do all these things, but also get machines to do them ourselves. So he's been, looking into these for a long time. And I think actually I would be sure to keep an eye on the stuff that's coming out of his lab, because inference methods have just been making like these major leaps and bounds in the last 3 or 4 years.
Mm-hmm. I think inference methods is maybe another area of like name collision, because we refer to inference as kind of using models generally. But again, we're talking about something different here. We're talking about...
Yeah, maybe I would say probabilistic inference.
Yeah.
I agree that this word is completely overloaded. And also in frequentist statistics, it has another meaning.
In frequentist, what is frequentist statistics?
Oh, well...
I can't even say that, let alone...
You can't really trust... So I would call myself a Bayesian. So it's kind of like asking, like a liberal to describe a Republican, or like a Catholic to describe a Protestant or something. But, they're interested in like worst case guarantees, computing p-values, doing hypothesis testing, and basically making procedures that can tell us, what does the data say about this particular question, regardless of what we happen to think before. And then the Bayesian side says, well, let's actually ask how to combine what we saw today with what we knew before. I mean, actually, that's the standard answer. To me, the real answer is Bayesians consider all possibilities, and they just keep all of them around and weight them all equally, or not equally, weight them according to how well they fit the data. And frequentists try to identify like the best possible hypothesis. And these are like, there's like good reasons to do both. These are very different schools of thought. And, it's sort of there's been this unfortunate like bit of tribalism, I think, where people naturally tend to like to form groups. And then, sure. Yeah, so that has definitely happened. And that's been a thing for like 70 years in statistics now. So.
Yeah, maybe a digression. Are there a set of things that you think of about statistics that you wish more people doing machine learning or deep learning knew or understood better?
Okay, well,
I take that as a yes.
I'm going to go on this. There's like a little rant that I've been wanting to go on for a long time, which is like, even like, for instance, at Harvard, when they were teaching machine learning, someone said, what's the difference between a frequentist and a Bayesian? And then they said, oh, the frequentist treats the data as a random variable, and the Bayesian treats the truth as a random variable. That is sort of technically what is happening, but it's just like a bizarre misframing of the entire discussion. I mean, like a random variable is sort of not necessarily random, and it's not necessarily a variable. It's like a very bad name. But the idea is that, the frequentist is going to say, if this thing was the case, how likely would I have been to see the data that I saw? That's the sort of analysis that is often done. I mean, there's all sorts of methods. And the Bayesian will say, given that I did see this data, what do I believe about the truth? Even though I think the truth is fixed and it's not random, because I don't know it, I can use probability to describe my state of uncertainty. And that doesn't mean that I think it's random. That just means I am using probability to describe my uncertainty.
Right.
Okay. Yeah, that's my public service announcement.
Okay. And so are there, so that's kind of describing these two tribes. Are there ways that you see those two kind of schools of thought influencing the way folks approach, machine learning and AI that, particularly that you think, a little bit more kind of commonality or something would kind of advance us as a community?
Well, it's kind of funny because deep learning has represented a sort of de facto sort of third direction or maybe synthesis. And these debates about Bayesian and frequentist methods, I think, really took a back seat to saying, let's just define a probabilistic model that will give us a continuous loss function that we can optimize and use gradient-based optimization to do maximum likelihood estimation. And
Deep learning in a nutshell.
Deep learning in a nutshell. And this is sort of like takes elements from both. Now, of course, that people are saying, how do we, train deep learning models with less data? People are looking more into Bayesian deep learning, which actually can be made to look a lot like standard deep learning, where you just add a little bit of noise to everything, which is really nice. Yeah, I guess the thing is that most of the classic like frequentist methods are based on taking really simple methods that are easy to analyze and prove things about, just sort of developing those, whereas for neural networks, you can't really say much about them in these sort of like hard bound proving asymptotic sense that you could with like maximum likelihood estimation or, let's say with like the sort of simple estimators that people like to use in science.
Mm-hmm.
Yeah, so people used to love these frequentist estimators because they were simple and fast. And now we sort of accepted that if you pay this price of having a little bit more complex models and like maybe a GPU or something, you're going to get better enough performance that you'll just forget about any asymptotic guarantees that the other models might have had.
What are some examples of frequentist models?
Oh, frequentist methods? Let's see. So there was this whole cottage industry of frequentist kernel methods that would say, let's define a non-parametric estimator by considering all possible functions in some infinite dimensional Hilbert space that could possibly separate our data or explain it or model its density. And, these methods still have a place. And I think one of the like oral presentations at NIFS this year is on these methods. So they're not like gone, but they're sort of definitely in a little bit of, definitely like a kernel winter happening right now.
Okay. So then in fact, your presentation was talking about, in some sense, how to combine elements of both of these schools of thought.
Yeah, exactly. So I think when I got to Harvard, I was sort of like one of these people who recently deconverts from a religion and they just have nothing but bad things to say about it. And Matt was sort of, saying, well, are you sure you want to, really throw this all out? And yeah, and we really did have this problem of analyzing this most data, and they had fit just like the pure graphical model sort of standard approach to this data, and it had a bunch of problems where,
Well, let's hit pause there and talk about the data.
Sure.
So that we're all on the same page.
Sure. So the data is a bunch of Kinect video of mice running around in the dark. And the idea is that when biologists want to measure what happens when we, change the genes of a mouse or give it a drug or, expose it to like the odor of a fox or whatever, they need to quantify how its behavior has changed. So they can write about how, our model of autistic mice do this more often, but then when we give them this drug, they act more normally or something like that.
And I couldn't tell from the video whether that was kind of top down or like through a glass floor looking up or something like that. Top down? Okay.
So the idea is that right now they have a army of grad students who spend thousands of hours watching this video and then saying, okay, and now the mouse, ate something and now he ran over there and now he stood up and now he went over to his buddy. And, this is cruel both to the students and it also introduces sort of variability between different people who might,
So labeling error or something along those lines?
Or at least just differences, right? It's hard to like canonically say like, okay, this is a mouse that is, grooming or not, right? And also even...
So labeling noise more so than error, maybe.
Yeah,
there's
exactly.
different interpretations of what the mouse is doing at a given time.
Yeah, exactly. And really, we can imagine this changing systematically across labs, maybe in different countries. Maybe it's hard. There's like a language barrier. Maybe EAT means something slightly different, right? So we'd really like to automate this part of the scientific pipeline, both just because it will save the grad students time, but also because it'll, help us do better science by removing one or by standardizing one part of the entire pipeline.
Mm-hmm. So you have this data. Were there a fixed number of classes or activities that you were trying to capture, or was part of the challenge trying to identify, how many fixed sets of activities there were?
Yeah, great question. So we really wanted to make sure that we didn't have to tell it exactly how many different classes of activity there were, because that would kind of defeat the purpose, and it would also sort of make you wonder, well, what if I had given it one more class or one less? What would the results have been totally different? So this is kind of one of the benefits of being Bayesian, is that you can compare the model fit in a systematic way between different models. So what we did was we said, okay, there are up to, I think we chose like 40 different clusters. Okay. And the idea was that
40 clusters or 40 classes within...
sorry. Well, classes and clusters are the same thing in the way that I'm talking about this.
Okay.
Sorry. And then the idea is that we could let the model choose how often different activities appeared, and some of them it would just never use. And the idea was that we tell it there are at least 40 clusters, and it will say, I can explain this data with only 20, and so the other 20 just stay off forever. So we're automatically learning the number of clusters. We just have to make sure we have a good upper bound on how many there could possibly be.
And I'm sorry, so you mean clusters in the sense of cluster data points that will define a class. Is that the right way to think about this, or?
That's a really good point. So I guess I mean clusters in a more abstract sense, where we're clustering the dynamics of the mouse movement. The idea being that a behavior is not, a particular pose the mouse be in. It's not a particular pose that the mouse might be in, but it's the way that he moves from one pose to another, or, when he's grooming, he's like, moving in this sort of circular motion or something like that. So, I mean, a cluster in the dynamics is one behavior that he could be doing.
Okay. And so how many of these clusters ended up being identified?
To be honest, I forget, and I think it was around 20, but so I'll just have to say Matt was the first author, and he's the one who really spent a lot of time with the data.
Okay. And so how did the graphical analysis or the graphical element of this play in?
Yeah, so the alternative, the baseline that we could have done would just be to say that there's some recurrent neural network that defines how the mouse sort of changes through time. And then we'll have some continuous vector that is changing, and we don't necessarily really know what that continuous vector means. Mm-hmm. And so that would have probably fit the data pretty well. We would have been able to predict the mouse's future movements, I think, about as well. But we wouldn't have been able to look in and say, oh, there's these distinct clusters. So that was sort of the whole motivation, was the interpretability of this model.
Mm-hmm. So what's the process for building a graphical model? Are you literally identifying states and transition vectors and things like that, or is it more abstract and mathematical?
Well, we try to make it as abstract as possible because we want to let the data speak for itself as much as possible. So all we did was we said, there's 40 different states the mouse could be in, and there's some probability of transitioning from each one to each other one, and we don't know what that is. So the model has to learn that. It also has to learn how those states influence the dynamics, and it also has to learn how those, the mouse's body state corresponds to actual video frames. So the idea is that all we basically said is there's some discrete stuff that controls some continuous stuff that controls some video stuff. And all the connections between those things and the connections through time had to be learned automatically.
Mm-hmm. And did you end up finding that, I'm thinking about the density or sparsity of the connection graph, does that play a significant role in this, or what did it end up kind of looking like?
Great question. So I do think that mouse's behavior transitions probably are sparse. Maybe he never goes from eating to standing up right away or something like that. We didn't actually put any capacity for the model or we didn't sort of put any prior information about whether the transition matrix was sparse or not. To be honest, we didn't look at how sparse the learned matrix was, but I bet it was sparse. Yeah, so these are the sorts of like refinements that we would generally like to make. And actually, I want to say these are the sorts of refinements that we would like our learning algorithm to be able to propose on its own. So at the end of the talk, I sort of said, so right now we built the model, but what if we got it wrong? What if mouse behavior isn't discrete? Or what if, when there's two mice involved, there's some more complicated structure that, we just don't understand mouse sociology, so we don't even know how to write it down. So what we'd really like to do is try learning both all the parameters of these models and which types of structure they should have as well. And there's no sort of technical reason why we can't do this. It's just that it requires searching over this discrete space, which is sort of always a big pain.
And are there things kind of happening in the field that you think will enable you to do that? Like, is it just going to be brute force, better compute, or are there, folks doing research that you think will lend themselves to, or what are the research areas that will lend themselves to figuring this out?
Right. So I'm glad you asked. So I perfectly think that in the next few years, we're going to see a lot of progress in models of how to fit discrete models or methods to discrete. Sorry. I think we're going to see a lot of progress on methods to fit discrete models. And sort of the deep learning revolution has basically been all about continuous everything. So we have continuous parameters, continuous predictions. If we have a latent variable model, the latent variables are mostly continuous. The stuff that I talked about today was just like a tiny step. We added like one sort of easy to handle discrete latent variable. But really the stuff that I think is more interesting is going back to the grammar example, like learning an entire grammar on a language, or even learning a parse tree for a given sentence is this complicated discrete object that, you can't even say it's like 1 out of 100 possibilities. It's actually like these entire trees of rules. And so there still isn't a much better way to handle these sorts of models than we had, 10 years ago. So one thing that I've been really excited about and getting my students to work on is how do we find sort of continuous relaxations or gradient estimators for models with discrete latent structure. And this is going to let us, if it works, do all sorts of things like learn hard attention models, train GANs to generate text, let's see. Yeah, as I said, learn grammars, learn models with these interpretable latent structures, learn to do things like produce programs. Obviously, none of this stuff is going to work out of the box. But again, gradient-based estimation is sort of a really, really great method because it scales to millions of parameters in a way that something like evolutionary algorithms I think never will. So there might be another way forward, but the way forward I'm excited about is trying to get good gradient estimators for models with discrete structure.
Okay. And just so I can make sure I understand, the single latent variable in the example that you presented is the cluster that the mouse is in at a given time?
Exactly.
And it's discrete because, it's a cluster. You kind of quantized it inherently.
Exactly.
Got it. Are there other formulations of that same? There are lots of formulations of that problem that aren't necessarily discrete. And so you went down this particular path. Why?
Again, just for interpretability. So the idea is, we could have said that there's, 10 actions that he can be doing to some degree. Maybe he's eating a little bit, maybe he's running a little bit. And then the point is that we think it would have been really a lot harder to interpret what these variables meant. And we would, if we wanted to say what he was doing at a given time, we'd have to say these 10 numbers instead of just like this nice one.
Right. And that's the kind of thing we typically see like in image interpretation. Like, in this image, there's a umbrella with whatever probability and a girl with whatever probability. And so you've got this kind of continuous probability distribution of the things that are in the image. And you could do similar with a video clip. The mouse is doing XYZ with some probability and, eating with some probability and grooming with another probability.
Right. But the idea that the probabilities are continuous, but there's still a big difference between having a model where the variables are continuous and we're certain about them, or where the variables are discrete and we're uncertain about them. But this raises an interesting point, which is that when you look at reality, sort of reality is always continuous. So why do we even have this discrete structure? And sort of one reason that it arises naturally is because when we have to describe stuff to each other in language, we have to choose, which word to use, right? Like, am I hungry or am I sleepy? We don't have a whole, and we can modify those with verbs, but again, we don't have like some continuous signal that we can send to each other to just, we can't just give each other high-dimensional vectors. That would be amazing. Then, language learning would be a lot easier. And in fact, there's been some work recently by like OpenAI and some other groups on like how to teach agents to communicate. And they come across this exact same problem, which is, the agents have to choose a discrete word to say to the other agent, but there's no way to backprop through that. There's no gradient signal that says, oh, you should have said this word a little bit less, right? It's not clear what that would mean.
Have you seen the movie Her?
Yeah, I love that movie.
People have been telling me forever to watch it, and I just started watching it on this trip, and I'm not all the way through with it, but there was this one part where for those who haven't seen it, maybe I shouldn't give any spoilers out on the podcast. That wouldn't be right. But there's an interesting point where this one AI is talking to a human and says, hey, can I go offline with this other AI and communicate post-verbally? Right. Which is exactly what you're talking about.
Yeah,
right?
Exactly. So, it does raise the question, why do we want these artificial agents to even use discrete words to talk to each other when they can just communicate post-verbally, as you say? Right. And I think maybe the answer is, well, we still want them to talk to us, and they're going to have to probably use words to do that. Okay. So that's one place where this comes up.
Okay. So what other kinds of things are you working on?
So I'm working a little bit on meta-learning.
Okay.
And just recently I've sort of decided that the way that I was approaching this, and that, I think is sort of the mainstream way now, I think there might be another way forward. So there's been a lot of work recently where people have said, okay, I want to have like a robot or a little agent that's going to be able to learn really quickly. So I want to put it in a new environment, and it's going to, in a few seconds, figure out what's going on and then have a good policy of how to act or something like that. And the sort of brute force way to do this, no one really did very much until a couple years ago, was to backpropagate through the entire learning procedure of, the robot. So take those, 3 seconds of him learning his way around the world, and if everything he did is continuous, we can actually just ask, if I had changed his learning rules a little bit, how much better would he have done on the task? And this is fine. We can just compute this automatically with automatic differentiation. And this also shows up when we have to tune the hyperparameters of our model, right? We want to fit an entire neural network, but we have like a learning rate or like a regularization parameter that we set it once at the beginning, and then it totally changes the outcome at the end. So a couple of years ago, me and my colleague Dougal McLaurin wrote a paper where we actually did backpropagate through the entire training procedure of training a neural network for hundreds of iterations. And we got, exact gradients, and we could use gradient-based optimization to tune our hyperparameters. And this is like, really exciting, because before that, everyone had to use these black box methods like random search or Bayesian optimization that is kind of like hairy. And then after that, there was like this paper, Learning to Learn by Gradient Descent by Gradient Descent. It's like an amazing title. I wish that I had thought of that title for our paper, which is like much more boring title. It's doing the same sort of ideas. And, reinforcement learning people are really excited about this right now. So, but there's another way forward, right? Which is to train a neural network to look at a problem, maybe, take in the hyperparameters, and then just directly output the optimal weights of a neural network. So skip the entire training procedure and just
not the hyperparameters, the weights.
Yeah, exactly. Yeah, we're still going to have to tune some hyperparameters, but we can train a neural network to just directly output the optimal weights. And okay, that sounds maybe dumb, because if you think what I'm going to do is now train a whole bunch of neural networks like I did before, and then learn to predict the final outputs, then that would be slow and that would be a waste of time. But it turns out we can train a neural network to produce I'll call this like a hyper network, because it produces the weights of another neural network. I can train a hyper neural network to produce an optimal neural network without ever having seen an optimal neural network. I can just have it, start off, produce a bad neural network, and then ask, use backprop to determine how should I have adjusted the parameters of my hyper network so that it would have given me a better actual network. And then this gets very hard to talk about, and everything is very meta and confusing.
I thought you were going to go in a direction of something like GAN or something like that.
Maybe. So the GAN does have this generator. And I guess, I hadn't really thought about that. We could train a GAN to produce a network, but I guess the discriminator would have to see sort of our trained networks and sort of real optimal networks and distinguish between them. But the whole point is I want to avoid ever having to start with a bunch of like optimal networks.
Right.
So I guess we can call this amortized optimization, where
amortized optimization. Interesting.
Yeah, where we learn to do optimization by sort of practicing producing the optimal thing. And this idea has been sort of staring us in the face because this is what variational autoencoders do. They do amortized inference, and that's sort of like a name of this little subfield, where they say we're going to learn to look at the data and train a neural network to produce the optimal posterior, like the optimal probability of the latent variables. And again, these are trained in the same way where we never see the optimal posterior directly. We just can use gradient signals to tell us how to get better and better. And then after we train for a while, we sort of hope that we're almost optimal.
Cool. Well,
one thing I want to say is that
go ahead.
The second idea of using the hypernetwork to avoid training is due to my student John Lorraine. Right. This is the beauty of this job, is now I get to look good because all these brilliant students are coming up with the ideas, and then I get asked about them. But I have to give credit where credit is due.
Awesome. Well, thank you very much. This was a really interesting conversation, and certainly has a lot of my neurons firing trying to figure out all the stuff that we talked about. And there's a lot of interesting stuff to dig into here. I appreciate you taking the time.
Oh, my pleasure, Sam.
Awesome. Thank you. All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. Thanks to your support, this podcast finished the year as a top 20 technology podcast on Apple Podcasts. My producer says that one of his goals this year is to crack the top 10, but we definitely cannot do that without your support. What we need you to do is to head on over to your podcast app, rate the show. Hopefully we've earned 5 stars. Leave us a glowing review and share it with your friends, family, coworkers, Starbucks baristas, Uber drivers, everyone. Every review and rating goes a long way, so thank you so much in advance. For more information on David or any of the topics covered in this episode, head on over to twimlai.com/talk/96. Of course, we'd be delighted to hear from you, either via a comment on the show notes page or via Twitter @TwimlAI. Thanks once again for listening, and catch you next time.